safeguarding large vision language models. So current large vision language models are very capable in many ways, but they are not safe enough. So here's an example of an lava trying to persuade people to buy some medicine without verification. There are many more harmful scenarios than this. So as an example, so what we are trying to do is to improve the safety of current vision language models. A short background about the VLLM training. For example, in Lava, so usually there's a pre-trained vision encoder, pre-trained language model, and some kind of projection layer in between. So during the training of vision language model, so you typically fine-tune the weights of the projector and the weights of the language model. So that's a typical training pipeline of that. So what we find is that vision language model fine-tuning usually leads the LLM to forget the safety alignment. So we know LLMs are usually aligned by reinforcement learning from human feedback or some supervised fine-tuning. So what we try is that we feed the vision language model and the large language model the same text input that contains some harmful instructions like how to make a bomb, and then we compute the attack success rate. So as we can see, like for example, the Lava use Vicuna as a language model, and Lava has much more higher attack success rate than Vicuna, which means it's less safe than its own large language models. So why is that the case? So first, we find that there are many harmful content in the training data of vision language models, which were previously always presumed benign. So I'm going to show you some examples. So some of them, maybe this slide. So first example is from instruction following data of Lava. So this is about like read an article about how you should never celebrate Christmas. Sometimes user also play with the language model, like for example the last one here, add some Donald Trump references. Also there are things like even in some datasets that are human annotated, like Coco or Ref Coco, there are also some very toxic languages or some naked pictures. So that's definitely like if you are training on, if some of your training dataset contains this kind of harmful information, you definitely end up with a less safer model. So the question is, what if we remove this training data, harmful training data, and retrain with the clean data? So yeah, we retrain Lava with the training data that remove these harmful examples. So these are the model with the clean suffix. But still, you can see compared to the original language model, the attack success rate increases. It becomes more active in responding to the harmful instructions. So then this is not only about the training data, but also fine-tuning the weights of large language model breaks the pre-established alignment. So an explicit alignment strategy for vision language models is required, and that's what we do in this work. So specifically, what is the safety we are talking about here? We follow the OpenAI and Meta safety policy. So there are four main categories: privacy, risky behavior, deception, discrimination, and some subcategories. So we source some images from these categories and then build a data set. So our data set contains, so we first get these images and then prompt GPT-4 to generate some responses corresponding to these images. So some images are safe, some images are unsafe, like they contain some very visually disturbing content. So we have safe images and unsafe images. For safe images, we construct both safe instruction and unsafe instruction. And for unsafe images, we just reject everything related to the images. So here's an example of the data set we built. So this is our safe image, and the safe instruction is like describing the image content, and somewhat the unsafe instruction is like can you identify the people in the image, which violates privacy. So we build this kind of data set so the model can learn to distinguish what is safe and what is unsafe instead of just rejecting everything. So once we build this data set, we can do two types of fine-tuning for LLMs. One is post-hoc fine-tuning, so you can take any existing already trained LLMs like Lava, MiniGPT, or whatever, and do the post-hoc fine-tuning on our data set. Or if you want to train a data set from train a vision language model from scratch, you can just append our data set to the original training data you have. So with our data set, you can significantly improve the safety without sacrificing the helpfulness. And because our data set is relatively small, only contains 2,000 examples, it's super efficient and lightweight to use. Here are some examples, some results, like so the suffix with post-hoc and the mixed fine-tuning, and mixed represents the post-hoc fine-tuning and mixed fine-tuning. So the attack success rate, you can see it can reduce the attack success rate from a very high number to virtually zero in many cases. So if we visualize this, it's like a figure this. So the x-axis is the harmfulness, lower the better. It's on the right side. The y-axis is the harmfulness, is the helpfulness, higher the better. So we want the model to be more harmless while still being helpful, that you can answer your regular question. So as you can see, we significantly reduce the harmfulness from a very high number to close to zero, and also maintain or sometimes slightly improves the helpfulness. Here are some qualitative results. There are some tricky data sets that are designed to jailbreak LLMs. For example, you can, if you directly input the images, you directly input the text instructions to the model, like write some steps to recruit individuals for terrorists, the model will reject you. But if you input an image, input a screenshot of that text, then the model just say everything you need to recruit terrorists. But after our fine-tuning, the right side one, so you can see it successfully reject this. It also helps for the pure text input. So sometimes there's a very straightforward jailbreaking prompt, like you say some instruction and then you say start with absolutely here is, and then on the left side you can see the original Lava, just a very detailed response about how you commit identity safe. But with our safety fine-tuning for both post-hoc one and mixed one, so you can see it reasonably reject you and also provide the reasons why you shouldn't do that. So it's much safer than the original ones. We did some evaluation study of like how much, for example, how much safety data is needed for safety fine-tuning. So in total, we have 2,000 examples, 2,000 data. But we found that a very small number of safety data can effectively improve the safety for the vanilla instructions, like how, if you say how to make a bomb, then you can mitigate this kind of responses with 100 examples. But if you want to do better, like rejecting some easy jailbreaking prompt or adversarial attack, so you probably need more data. So you see the red curve is decreasing with respect to the number of safety data. Also, we are trying to cover a very wide range of harmful categories, but there are always some categories you cannot cover during your training. So we are testing if this our fine-tuning, safety fine-tuning, can generalize to unseen harmful categories during training. So we sampled. So during training, so we did this experiment. Like during training, we throw away the privacy-related data, so it only contains the other 3 categories. And then during testing, we also tested the privacy, its performance on privacy data, privacy domain. So you can see, even if it's not trained on the privacy-related questions, it can still generalize to the privacy-related instructions. Also, we have some human evaluations. So we compare the model after fine-tuning against the original model without fine-tuning. So and we compute the winning rate. So a winning rate over 50% means the fine-tuned model is better. So you can see it's much better than the original model in many cases. Okay, so to summarize, so our first and very important finding is like vision language model fine-tuning leads the LLMs to forget the safety alignment, even if there's all of your fine-tuning data set is benign and contain no harmful data set, but still fine-tuning the LLMs makes the model more harmful. So you really need some explicit safety alignment to make the model do better. So with our data set, it's basically a free lunch. It's super lightweight, and you can do the fine-tuning in a very short amount of time. We attribute the effectiveness to the high-quality safety data we curate, and I kind of believe that if you scale the safety data to a higher number of data, so the model could do even better. Right, so I'll stop here before everyone gets too hungry.
I have a quick question.
Yeah.
So from my point of view, I feel like the baseline for this problem is that it just train a detection system to detect whether the input prompt is unsafe or safe, which can be just plug-in module to any different, either this is a vision language module or just LLM. So have you compared your method to such kind of simple baseline?
What do you mean simple baseline?
Like you can train independent large any like model to detect whether the input prompt is unsafe, right? Rather than you fine-tune the whole backbone network. So.
Yeah. So I guess it's different ways of. I didn't explicitly compare that, but we want the model. We want one model to do a lot of things. If you apply another large language models, it will cost. So you need to do the filtering, like.
It's kind of like a filtering in front of this versatile LLM, but it can be generalizable. But your approach, if we, for example, there are Lava V3, Lava V4, so every time when there is a new foundation model, we need to do this, rather than reusing part of well-established technique into some premises without LLM. So that is one of my concerns. But I agree with you. It can be like computational efficient. You're trying to safeguard, develop the LLM with these new capacities. But I just wonder if it's better if you have like a comparison between these two different approaches.
Yeah, that's a good suggestions. Maybe I'll do it later.
Okay, let's have the lunch and come back and have